Hi, everyone. I'm going to be talking a little bit about using new features of modern CPUs, specifically tracing features, to detect malicious files, to detect exploits. Before we get to the interesting part, a little bit about us. Both with offensive background, both no longer dealing in offensive technologies. I work as an independent security researcher. I've been doing mostly defensive work, defensive research. Some of you may have read my bio and the news last night. So I did used to work for NSO, but I no longer do. I've been out of NSO for about 3.5 years. I don't know much about that. Okay, so what will we be talking about today? I'll be talking about the project and the research that we performed during 2015. And the goal of the talk will be to walk you through the project, through my eyes as a developer, through the obstacles encountered, and through the various solutions we found to different obstacles. The idea being that eventually after this talk, you should be able to implement the whole project on your own. You won't have to because we'll be releasing the code sometime 2016. But you'll see the whole process we went through stage by stage. I'll be starting with a small introduction about what processor trace is, what control flow integrity is, how we use it to detect code reuse or other types of exploitation, and then we'll do a drill down into the different parts of the project. So a little bit about the project itself, developed independently, not affiliated with any specific company, not sponsored by any specific company, using a new CPU feature, a modern feature that exists in new CPUs called processor trace, where the overarching idea is taking a document and detecting if it contains an exploit, a document or some kind of other content such as a Flash applet or any type of content that can be parsed by an application. Very simply, what we do is we trace a program, we analyze the trace, and we detect if the file contains an exploit. When I say trace a program, I mean we take, for example, Adobe PDF Reader, we give it a PDF, we perform a trace, and then we can analyze this threat and detect exploits. Specifically for this project, we focused mostly on the tracing part. We want to provide a framework for control flow integrity implementations. And as an example implementation, we implemented a shadow stack. Right? This is a backward edge CFI method that can detect any type of ROP, code reuse, return-oriented programming. I won't be talking so much about theoretical or the future of exploits, whether ROP is dead, whether CFI is the future, stuff like this. This is, I think, better for offline talks, but focusing on this specific project. So when we set out, we had several requirements for the project. Highlighted are the main ones. We wanted this to work on Windows-based applications, Windows-based machines, since these are the common enterprise machines. We wanted a full trace of the program flow, right? So we wanted to trace every part of the program and be able to reconstruct the complete flow of what a program does. We wanted to be fast, okay? We want this to be a practical solution, and we want it to be non-intrusive. Non-intrusive meaning given an information leak or something similar, an attacker won't be able to detect that this is being performed on a specific application. We also don't want to have any kind of compatibility issues, and when we are non-intrusive, we immediately discard that problem. There has been quite a lot of previous work on the use of CPU features to detect exploits. This is a non-complete list. The work by Fudan University is a big part of recent work. Endgame presented in Black Hat this year, also quite impressive. Most of these approaches use what is called the PMU, the performance unit. And the approach we use is slightly different. So it's not directly related to any of this previous work, but it's sort of in the same realm. So just to get a map of where we are. When we talk about the exploitation process, there's different ways of dividing this, but we have the pre-exploitation process, we have the exploitation itself, and then everything that happens after the exploitation. We obviously want to try and stop the exploit as early as possible, because that allows for less wiggle room and less place to play for the attacker. That pre-exploit is pretty hard. You have to have prior knowledge of the exploit or use some kind of heuristic, which is why a lot of work is focuses on the exploitation stage itself before the malware can try and evade, but as early as possible. If we're talking about anti-exploitation methods, we have the traditional anti-exploitation methods such as ASLR, later EMET. We have emerging anti-exploitation methods such as Microsoft control flow integrity and Intel control flow integrity. We have the PMU events I talked about. Also, nobody knows exactly what will be with them, but also emerging. And of course, some application-specific anti-exploitation methods. So where we are is somewhere next to the PMU events. Right, this project talks about a method that, as far as I know, hasn't been described before and sits somewhere next to the PMU events. Contrary to CFG and CET, this is a non-mainstream company pushing this to all platforms on the one hand, but on the other hand, it's something immediately applicable. So, what is control flow integrity? Very simply, control flow integrity means making sure the program flows as intended. This is something that has been talked about a lot, but often deemed impractical. It's deemed impractical because existing ways to do this have either been to use compiler-based, right, intervention in the compiler toolchain, in the compilation toolchain, or dynamic binary instrumentation-based. Both of these have different types of disadvantages that make control flow integrity not very practical usually. A few new initiatives looks quite promising. Microsoft, as I said, Intel, and some commercial companies. Okay, to perform CFI, we need two things. We have to do two things well. We have to have a way to get the program flow, and we have to have a model to define how the program should flow. Luckily, compilers, linkers, they write programs, right? So people don't write programs, compilers write programs. So we can assume all kinds of truths about programs, such as functions should return to their caller, right? People don't have to write software that way, but compilers, well, usually write software that way. The main focus of this talk and the main focus of the project itself is how to get the program flow, right? Because once you have the program flow, this is the technologically challenging part. After this, there are many theoretical implementations of CFI, forward edge, backward edge, different types of analysis that can be performed. So the focus is how do we get program flow in a practical, non-intrusive manner, as I said, on a Windows machine. Come in, Intel processor trace. Really cool feature. It traces every instruction a CPU executes in real time. It traces it to a memory buffer and can be enabled by software. A compressed trace, which means we don't have to deal with gigabytes of memory unless we have a very long trace. Low overhead. Documentation says 5% or up to 5%. In effect, it's actually quite a lot lower because applications spend a lot of time in I/O, user interaction, stuff like that. So it's actually just 5% overhead on actual CPU execution. I think this has improved with latest models of CPUs. And very importantly, it supports filtering by process. It doesn't allow a lot of operating system context, but it does allow filtering by the CR3 register. It's available starting with Intel 5th Gen CPUs. It's the successor of the branch trace storage. I say successor because it's a similar feature, but they're actually very different. The branch trace storage would make a program run 40 times slower, while Intel PT, processor trace, has a 5% overhead, which is very, very different. I also put a star next to available in Intel 5th Gen CPUs because if you read the documentation carefully, You might deduce that it has been available before, but wasn't documented. I don't actually know if this is true, but it seems to be the case when reading the documentation. So, how do we use Intel processor trace to detect a malicious file, detect an exploit? In very simple words, the trace gives us every instruction in the program. Analysis of the program gives us the control flow model which we should be watching for. For example, every function should be returning to its caller. We can verify that the program does as it is intended to do and does not do things that it is not intended to do. And we detect malicious files. Okay, so obviously it's not that simple. Several different challenges that we have to overcome. First is how we analyze processor trace. How do we handle models and threads? Do functions always return to their caller? If they don't, how we handle this? Does Intel PT even work? If the question is up there, then it probably doesn't always work. And the major obstacle or the major challenge of analyzing processor trace is how long it takes. You'll see that there was quite a lot of effort put into this. So how do we analyze a trace? The format is compressed. It only contains information that has to be contained within the format, and so it assumes a memory map of the program. This means when you analyze the trace, you have to have the disassembly that was running, you have to have the exact memory outlay and the exact bytes in every address of memory while the program was traced. So you take a memory map, you take the trace data, you disassemble the memory map, and you have the program flow. This is the general architecture of how trace is performed. It's based on 9 different packet types. We're not going to go into each and every one of the packet types. 2 are of more importance and are basically the packets used to perform a trace. These are the TNT packets and the tip packet. TNT packet is a packet that will tell us for every conditional branch whether the branch was taken or not taken. Everything else, as I said, we can deduce from the assembly, right? If the branch was taken, we can deduce the next address from the disassembly. And the tip packet, which tells us the next address for every instruction for which we cannot determine the next address, right? If we have a far call the AX, or call for memory address, or something of the sort, we can't determine the next address, and so we need a packet to tell us what the next address is. Okay. This is what the packets look like. Once again, we're not going to go into too much detail. A tip packet contains the tip signature followed by an address, very simple, and the TNT packet contains a number of bits, each bit corresponding to one conditional branch, right? So every bit will be either 1 or 0, and this will tell us if the branch was taken or not taken. Pretty simple. You can also see that the tip packets have a length. This is a method of compression. If the target or some bytes of the target are the same as the previous address, they will be omitted to save space. So, okay, I'm gonna discard this. How do we analyze the trace? We take a start address. The trace, the Intel PT trace gives us a start address, and we start by disassembling. We disassemble an instruction, and we check if the instruction is an indirect branch. An indirect branch or a far branch, any branch for which we do not know the next address. Interrupt would also fall into this category. Returns would also fall into this category. So if this instruction is an indirect branch, we look at the next tip, and we go back and disassemble. If this instruction is not an indirect branch, but it is a conditional branch, we look at the TNT bits, and if the TNT bit is set, we calculate the next address based on the disassembly, and we go back to disassembly. If the TNT bit is not set, we simply continue to disassemble. So, very simple, naive implementation. This is the by-the-book way of analyzing Intel processor trace. Okay? Next, we have to deal with models. As I said, we need a memory map to perform this assembly. We need to know what we have at each address in order to be able to perform that disassembly step. However, obviously the memory map in any modern operating system does not stay constant throughout the life of a program. Models get loaded and unloaded. Often they get loaded and unloaded at the same addresses or in overlapping addresses. And so we have to have a way to, A, get model loading and unloading, and B, sync model unloading and loading to the trace. So is the ETW, Event Tracing for Windows API, quite an ugly API to use, one of the ugliest Microsoft has produced. In order to get model loading and unloading, and the trace itself in order to sync the model loads and unloads between the trace and the model loading and unloading. So we actually can see every time the trace reaches an anti-load library or similar functions that cause a model loading, and then we can load the required model into memory, which we have on disk. That's about it. This is a screenshot of what model loading and unloading looks. Timestamps of the loaded models and the names, addresses and names of the loaded models. You might see some models appearing twice because they might get loaded. Well, this is the start of a program, but sometimes you can see the same model being loaded twice because it gets unloaded and reloaded at different addresses. So we take this and we sync it with the trace based on the trace information itself on the address, on the program reaching anti-load library. There's no need to sync the unloads, since every time we perform a load, we perform all the previous unload methods. We also need to be able to handle threads. As I said, Intel processor trace does not have any operating system context information, and we want to reconstruct the flow of the separate threads separately, obviously. We also want to have a shadow stack to know if we returned to the correct address after every function, and for this we also need to have to reconstruct the flow of specific threads. So there's a few approaches how this can be done. We attempted event tracing for Windows as one approach. Timestamps were not correct enough in the trace. I believe maybe in 6th gen CPUs they'll be better. There's some enhanced features, enhanced timestamp features. But what we ended up doing is using a lightweight driver, hooking context switches in the kernel, and then using more exact timestamps to sync this with the trace. I have seen other approaches, specifically using APC methods, queuing APC methods to every thread all the time, and then syncing on the execution of this specific APC thread on Windows. Some advantages and disadvantages to that kind of approach. So, when we want to analyze Intel PT, you can see that Intel supplies quite a lot of support. There's Linux support in the kernel, in perf and in GDB for Intel PT, mostly written by Intel or some Intel-affiliated people. Some open source libraries, such as libipt for analyzing processor trace. Z is a disassembler, an Intel disassembler that can be used. Which makes sense. I never knew Intel had a disassembler, but it does make sense. And both of these are free software, more or less. Intel also went through the trouble of combining these two, of taking libipt and Z and creating what is called PTZ. This is a simple open source analysis engine for Intel processor trace. It assumes a static memory map and a single-threaded application, but it sort of works. This is the output of PTZ. I'm sorry, this is not the output of PTZ, actually. This is the output of PTDump. This is just a representation of the packets, the trace packets you can see. The exclamation marks and dots are the TNT packets, right? So every exclamation mark is a taken branch, and every dot is a not taken branch. And the tip packets have an address in them. Okay. Now some numbers. Obviously, PTZ is not sort of robust enough to analyze a real application, which is multi-threaded and has a non-static memory map, but we want to know if it's fast enough. So take Adobe Acrobat, any version, and the large PDF file, and trace the parsing of that file. Several hundred megabyte trace, which doesn't sound so bad. Unfortunately, run PTZ on this file and you get to several hours of analysis. I say several hours, it might be days. I've never actually seen this finish. I never tried, because obviously several hours is not very practical. Now it is worth saying that Intel 6th gen CPUs support range-based tracing, so you can have a blacklist or a whitelist on the trace itself. This perhaps would save us time. A, it didn't exist at the time, and B, it would sort of undermine the requirement of full visibility into the program. So if we only trace part of the program, somebody could perform ROP on untraced models. Optimization. So this was a big thing for the project. We managed to bring down the analysis from hours to seconds using some optimization methods. Effectively making the analysis practical, right? So this is the main obstacle. Everything else can be overcome, but we do want to analyze files fast enough. Okay, so the main thing we noticed, and this is pretty straightforward, is that model code is static. We can also notice that we're not interested in disassembling most opcodes, right? If you have a move opcode, this does not affect the flow. If you have an add opcode, this does not affect the flow. We only want to look at branch creating opcodes, right? We want to look at call, we want to look at jump, we want to look at return, sysenter, stuff like that, okay? And so we only need the last instruction of every basic block. We don't need to disassemble. Is there any way of making this not flow on its own? It switches slides on its own. Yeah, just on. Oh, it's probably my PowerPoint. Okay. Okay, so we only need the last instruction of every basic block. Unfortunately, we can't find the last instruction without actually disassembling all the other instructions, right? Basic blocks don't just have the last instruction embedded inside the first instruction. And so we'd have to pre-analyze the basic blocks. Okay? Every basic block contains at most one branch, and so we can pre-analyze the basic blocks and somehow use this information to analyze the trace faster. Okay? We're essentially making a graph of the code or a graph of the basic blocks, and then we traverse the graph. If we have a basic block, we'd look at the taken not taken bit or at the tip bit, and we know what the next basic block to look at is. This can be done offline, takes a bunch of time, but it can be done offline, and then we can use this information in order to trace in real time much faster. IDA Python script over Python. This is what the output looks like, a bunch of basic blocks with the addresses, the length, their characteristics, etc. Unfortunately, this is not perfect. It's not perfect because IDA makes some mistakes. It's not perfect because some programs like to perform all kinds of anti-reversing tricks and jump into the middle of opcodes. And we have to have this perfect, right? So if we misanalyze a certain basic block and we don't have it in the graph, or the graph is incorrect, we're not only missing code, we can no longer perform the analysis. This breaks the state of the analyzer, and we have to have a perfect graph in order for this to work, or in order for this to work like this. Okay, so one thing is fixing simple IDA errors, right? All kinds of heuristics, flow propagation. Some errors are simple. Some areas still have errors, either because it's difficult to perform some kinds of analysis with IDA or some kinds of fix-up with IDA, or because the algorithms are not perfect, or because of anti-reversing tricks. So there's two things we can do. The first is we always have a backup mechanism with real-time disassembly. Okay? If we ever encounter an area which does not have a pre-analyzed basic block for that area, we can always go back to disassembly. This is also will sort of serve us later for dynamically generated code, which obviously cannot be pre-analyzed. And another thing we can do is, after we analyze with IDA, we can run the trace and see where we have errors, right? See where the code actually goes, but we don't have basic blocks for that area. and then we take the basic blocks that we saw in the real execution, and we put them back in the IDA analysis. And when we see that we're no longer missing basic blocks, we now have an exact basic block representation. So once again, we analyze the basic blocks in IDA. We start tracing the program. We see that we've missed some basic blocks. We see that the trace has arrived at addresses for which we don't have a basic block analysis. And we feed this back into the IDA analysis in a loop until we no longer have any missing basic blocks. If we do this on enough PDF files or in enough files for the specific application, then we reach pretty good results. So this is what the analysis now looks like. Everything you see in orange has been added since the last analysis. We take the start address, we look for our next address in our basic block database or in our basic block graph. We look at this specific data, we analyze it, and if we have basic block information for this address, we continue as we continued before. We look at this address. Is the last instruction of this basic block an indirect branch, right? So we're only dealing with the last instruction of every basic block. If we don't have this basic block in our graph, we'll be moving back to this assembly-based analysis, which is the slower analysis. But we'll only do this very rarely. So this improves a little bit on the analysis. Unfortunately, we have an extra stage here of looking up the next address in our database every time we have to look at the next basic block. Okay, so we can improve this. We did improve this. We improved this by relying on the fact that many branches are relative. Okay, many branches are inside the same model and they're relative. And relative branches, or so we assumed, don't branch intramodal. They usually actually don't branch intramodal, right? So if you have a jump 0 or any kind of relative based addressing branching, you know that they're inside the same model. So we can rearrange the basic block database so that different basic blocks are at the same relative address as they are in the real world. So if you have a relative branch from one basic block to another basic block, we're just calculating the difference and we can find the new basic block. This is always possible since we're actually storing less information in the basic block than the original basic block itself. We're storing the branch, but we're not storing all the superfluous disassembly. Okay? And we do this as long as the basic blocks are in the same model. So for every model, we store the basic blocks in the same order and the same distance as they were before. This further improves on performance. We now no longer have to look up the next model in our database for every basic block we traverse. We only have to look up the next address in our basic block database if the basic block is not in the same model. We have to check if the basic block is not in the same model only if we're using a tip, right? So we've taken this step, which is a very performance-intensive step, which we had to perform all the time. We're taking it out of the analysis, and we have a much more streamlined analysis. Okay? As a little implementation hack, we take all this information, we save it in a portable executable format, every basic block in its rightful place, every basic block in its correct relative address, and we've essentially built a little pseudo-assembly language that is easy to disassemble and only contains branch information. Okay, so this is an example. This obviously loads in IDA because it's a portable executable format. This is a basic block of the first basic block of an export of MSO DLL with the basic block information at the head, right? So this contains information about what instruction this basic block ends with, how long the basic block is, and we can use this information to perform a trace. Okay, so now we only have to perform lookups on intramodal branches. Having done all this, analysis runs in about 30 seconds to 5 minutes per file, closer to 30 seconds usually, which is pretty good. Okay, this is a big improvement on taking hours to analyze, and it's becoming sort of more practical. Okay, we can now take a file, analyze and construct the whole trace of the file, perform shadow stack checks, and detect ROP within 30 seconds to 5 minutes. But then I looked at what we're still spending time with. So still a lot of time in disassembly, quite a lot of time on the lookup between models and the shadow stack. These are all taking up quite a lot of time. Disassembly because of misanalyzed basic blocks, but also because of some dynamically generated code. I was working on Adobe PDF files, PowerPoint, and the entire Office suite. They used some dynamically generated code for graphics, was called the Warp, just-in-time compiler, and this obviously was not pre-analyzed. One way to optimize this is use a very fast disassembler. Intel Z is also not sort of suitable in terms of license. I really like the UDIS 86. It's great. It's hackable. Very permissive license. No errors. Really fast. I tried DStorm. I tried Capstone. This is what I chose for my specific purposes. It's very lightweight and maintained, but I really have to say this is a great product, UDIS 86. It was actually also the fastest disassembler. Okay, but we're still doing disassembly, and disassembly is always a performance-intensive operation. We're doing a little bit of disassembly, but we're still doing disassembly. So we can now rely on the fact that the code is different per iteration, but it will still run per iteration, meaning per execution of the process, but it will still run several times per process. So what we can do is we can patch the code so that the last opcode, the branch opcode of the basic block, appears at the beginning of the basic blocks. We can't always do this, but usually this will work. So if we have a long JIT-generated basic block containing a lot of mathematical operations, we can take the last opcode of this long basic block, put it at the beginning of the code, and we've essentially performed the pre-analysis or something similar to the pre-analysis in runtime and saved quite a lot of execution time. We could have also, okay, that's a presentation. If we have a long basic block, we take the jump instruction at the end and we put it right at the middle so we don't have to disassemble all the move instructions the next time we encounter this. Another thing that can be done, which is a little bit tricky, but is partial disassembly, right? These move instructions, even if we do disassemble them once, we don't actually need full operands for every instruction. We only need the length of instructions if they are not branch producing. Okay, so analysis after this stage takes about 10 seconds. 2 minutes is really a top time for very large PowerPoint files. The testing was done with some educational PowerPoint files with a lot of graphics. But most files run between 10 seconds and 30 seconds. And there's a pretty clear roadmap for further optimization. So I really feel that this is becoming practical, right? This is a practical way to analyze files and get a complete program trace and then perform CFI on this file. Worth mentioning, I never tried actually patching code in runtime without doing the pre-analysis. I believe this would probably be pretty fast, but not fast enough, probably under an hour. Okay, so a few other gotchas encountered, and a few other things that don't always go quite as well in real life as expected. Okay, so detours. So we supposedly have a working solution, but we do assume that the static models loaded into the process are indeed static models. Unfortunately, it turns out that quite a lot of applications like to put detours on themselves, either because of functionality enhancements, sandboxing, or other reasons. We can see this in Office because of functionality called AppV, app virtualization, or in Adobe because of sandboxing mechanisms. So since we pre-calculate the basic blocks, this will ruin our analysis, okay? It doesn't mean we can't analyze the detoured basic blocks. It actually means that if we assume the basic blocks are as we calculated them, it will ruin the state of the analyzer. So we can't sort of overlook this and just assume it will be okay. We have to fix this issue. Okay. Luckily, these detours are always at the same place. So we can take a memory snapshot of the process, add this info to our analysis, and mark these areas as misanalyzed. So we'll be disassembling these areas in runtime, which is a small performance overhead, but we won't be misanalyzing the code. We actually further improved on this by pre-analyzing the detours as well, which was a little bit tricky and saved very little overhead. So that's the way it actually looks in the code. These detours are actually pre-analyzed as well. So there's like another extension to the pseudo assembly that says, okay, now branch to detour number 1, and detour number 1 is pre-saved for every application and DLL pair. That's just a picture of I think this is Adobe, an anti-close detour. Okay, unnatural code flows. This was also a pretty big issue. We want to implement a shadow stack. So in order to implement a shadow stack, we have to assume, this is not fun. We have to assume that functions always return to their caller. Okay, if we want to perform CFI analysis, we actually use the shadow stack as part of the tracing mechanism as well. So the shadow stack has to work. So obviously, we started assuming functions return to their caller, and we found out that they don't. There's quite a lot of different mechanisms which make functions not always return to their caller. A classic example is exception handling, right? We perform some kind of stack unwinding, or we jump to a completely different location. But there's also quite a few other examples we encountered. These could, in theory, be sort of solved on a post-processing base, right? So we can mark all of these specific mismatches as false positives and just remove them from the analysis. But the flow is often more complex. So we handle these on a case-by-case basis, and we actually, inside the flow, have specific handling for each of these cases. Luckily, it's always specific, right? So per Windows major version, this has to be done once at most. For example, with exception handling, we often have a stack unwind to a certain address. We know this is legal, but we don't know how far up the stack we went if a function was called several times. Okay, so this is a little bit tricky and has to be solved inside the analysis. It's also a weak spot for CFI. So this area also had to be hardened because we have ambiguous states. At some points, we don't know how long the call chain is because we don't know how much we unwinded. And a little binary signature engine to keep all of this stuff sort of synced between different minor versions or different major versions of operating system and applications. Well, that's pretty straightforward, I think. Okay, another thing I mentioned is Intel PT doesn't always work as expected. Quite a few documented bugs, not so bad. Unfortunately, also some undocumented bugs, which cause quite a lot of trouble. I was working on a 5th gen laptop, one of the first 5th gen laptops to arrive in market. So this may be very model specific. It may have improved in 6th gen. Never reported it to Intel actually. And this may have improved. One specifically nasty bug happens specifically with Adobe DC or certain versions of Adobe DC. If a stack return address is modified manually by the code, if the code goes and puts a specific return address in the stack and some other pre-known prerequisites, right? This doesn't always happen. Then we will get a special TNT packet instead of a tip packet. This will completely destroy the analysis state, and this has to be handled. Once again, some reversing and some sort of case-by-case handling. Okay, so whenever we encounter a state error or state problem with our analysis engine. We go back, we disassemble the code, we see if somebody is putting a specific address on the stack with the specific characteristics that we've seen, and we fix the analysis. This was a pretty annoying bug because debugging is complex. We run quite a lot of iterations, and we never know what causes a context problem, an analysis context problem. It could have happened in the same trace, but many, many packets ago. So that's that. Results. We run this on several thousand Office Suite files and PDF files, several malicious files. For this corpus, it looks pretty good. Okay, 0 false positives, detected all the exploits. The exploits were simple exploits using ROP taken off Metasploit, but no information or prior information about the exploits was given to the analysis engine. And a cute little side effect is it actually shows the ROP chain, right? So one thing is knowing there's an exploit, but we can also show and prove that there's an exploit, and we can help say incident response or somebody analyzing a file or just learning to actually see the ROP chain or other CFI problem. Future challenges. So I'm going to talk a little bit about stuff that we didn't implement. We stopped there. This project was developed, as I said, during 2015. But there's quite a lot of work to be done. Might continue then now that we're releasing the code. So one thing is dynamic code generation. One thing I completely didn't talk about, and is pretty important. Okay, Adobe PDF, Office Suite, they use some dynamically generated code, but nothing too serious. This was handled sort of very simply. But some other applications like browsers, Flash, well, Silverlight, whatever, many different content parsers use just-in-time compilers. In order to have just-in-time compiler analysis, we'd have to have a snapshot of every time this code is executed. Okay, so one method is forcing a write XOR execute approach. You use memory page protections to force the page to either be writable or executable. And every time it becomes executable, you take a snapshot, and this is the model or the pseudo model that you will load into the analysis engine according to this timestamp. Very similar to what we did with models, except we have to actually implement the model unloading and loading ourselves. Something extra we can do is we can actually also take a snapshot every time, or a snapshot of the context every time the page is moved to write mode, and periodically since it is moved to write mode, and then perform emulation of the other threads emitting code to the JIT page. So we can actually see if JIT code is being emitted from somewhere where it shouldn't be emitted, if an exploit tries to write to the JIT page and then perform sort of legal code from the JIT page. This is, of course, somewhat theoretical because it's unimplemented, but I think this is one of the probably most prominent ways to go. There's a few other approaches that can be done. Time. Virtualization. Okay. So when I worked on this project, 5th gen CPUs, this did not support virtualized environments. 6th gen CPUs support virtualized environments. According to the spec, you should be able to perform a trace from the guest, from the host, or within the guest. It makes the solution more invisible, less intrusive, right? You can trace a virtualized environment from a VMM, from a host machine. And this is probably the way to go forward. This does need VMM support. So last I checked, Zen and KVM did not have support for interprocessor trace, but this can be added to the different solutions, either manually or by maintainers. A little bit about countermeasures, or how attackers will bypass these types of solutions. So, as I said, CFI is somewhat less effective on dynamically generated code because we don't actually know what the code looks like, because someone may have been emitting code that does malicious stuff without breaking control flow integrity. And also a few codes without code reuse are possible. I believe there's another talk later on today that talks about a similar exploit. There has been some work control flow bending. There has been some work on how to bypass control flow integrity solutions using only data modifications. Having said that, the CFI engine itself can be hardened, right? Given a strong enough platform that gives us complete analysis of the whole program trace, there's quite a lot of things we can do. For example, this is an easy example. If we have symbols, we can mitigate some use after free type bugs by forcing calls of virtual functions to only call into functions of the same inheritance tree. Okay, that's a sort of simple example of different types of CFI hardening we can do once we get a complete program trace. Still, of course, nothing will ever stop a fully unlimited read-write anywhere exploit. It's an open question whether a mixture of anti-exploit mechanisms and this type of anti-exploit mechanism will be able to completely stop exploits. Probably not, but I think this raises the bar. Thank you.
Any questions from the floor? Or questions off stage as always? Yeah? Well then, thank you very much, Shlomi and Ron as well.